When you're using a FFT-based audio analyzer software, then you might have experienced a problem. You need to understand what's happening in the software, understanding the software, as well as understanding all these steps to set up your PA system correctly. And in my experience, it took me years to understand all that. And today I want to show you my logic setup that I have built to better understand a system like Smart or whatever FFT-based software. I'm just using Smart here. You can use it with the software that you prefer to use. This video I'm gonna show you what I have set up here, and I would say you need to create a setup like this to experience and try things out offline, not on site, on production. They paid you money that you can do your job, and you have to do your homework at home. You can download this logic setup on my webpage, or you can just create the thing that you need for your productions. You may prefer another DAW. I just want to show you what's happening here. Exercise 1 is polarity and phase. So the first thing is, if I invert the polarity, this impulse here goes from positive to negative at the same time. Inverting polarity does not introduce any time. So if you say this is a phase reverse, or you're reversing the phase about 180 degrees, this is wrong. It's just a polarity for the whole signal. It's changing from positive to negative or vice versa. If you introduce a delay to the system, then it looks like this, and phase is related to a certain frequency. So you have to see here, for every frequency, the phase is changing now, minus 20, 30, minus 60, and so on. This is 180 degrees of phase shift. And if you can handle a calculator, then you might know this for 1K must be 0.5 milliseconds, and my impulse here approved this. And from here on, the phase goes around the wheel, and this is 270 degrees, 360, and so on. And the fact that the phase is going downwards, then you know that the measurement signal comes later than the reference signal. And let's bypass the delay, and we see here so a straight line in the phase view. And the impulse, let's zoom in here a bit, not minus, plus. So, if I change the reference delay to minus, so then the measurement signal comes later, and this means the phase goes down. And if I change the direction so that the measurement signal comes first, then the phase goes up. And so you know when the phase goes up, something in the measurement is earlier than in the reference, and vice versa. If it goes down, then you know that your measurement arrives later than the reference signal. Okay, so I bypass this, and now I come to the comp filter exercise. This is exercise 2, and if you unmute this, then you see a perfect comp filter. This is because I copied the reference signal, which is my generator here, and I have delayed the signal. And the question is, how much delay have I add to the signal? And you can see here that the first peak of the comb filter is at 100 Hertz and the first dip is at 50 Hertz. So if you can use a calculator, then you know that it must be 10 milliseconds. And if I zoom out here, I see a second peak here and second impulse at 10 milliseconds. And because the delayed signal has the same level as the measurement, the original signal, I have a perfect cancellation here. And if I change the level to -6, then you see that the dip first comes up and to the same value, -6 difference is the dip is -6, and here the peak is almost 3.5 dB, no longer 6 dB that it was before, but it's not decreasing that much as the dip comes up. And if I change to 10 dB, which is the next value what we're interested in, we have -3 dB of ripple, and if I change to -20, then I have, let's change this, so here, then we have a ripple less than ±1 dB. And this would be perfect for real-life measurement. Let's keep this in mind for the next exercises. I mute this group and come to the next one. This will show how coherence work. And some measurement systems, such as the Smart here, is able to show you the coherence. Therefore, I need some averaging, and if I press C, I can select if I want to see the coherence or not. What is a coherence? The coherence is your measurement signal divided by the measurement signal plus noise. And right now there is absolutely no noise, and this is why the complete the coherence is at 100%, which means there is no noise in the measurement signal that is not present in the reference signal. But if I add some noise here, this is a second is a test oscillator giving a second pink noise. This is not correlated to the reference pink noise here. They have nothing in common. Without that, they are both pink noise, but they don't have a. They are not in sync. Yeah, it's not the same signal. It's not a copy. And you see with because the level is the same. Yeah. You can see here the tendency for the magnitude is +6, and also the tendency for the coherence is 50%, which means it's the same signal level of noise than the measurement, the reference signal. So let's change this to white noise. Then you see that the spectrum is different from a white noise, and also that you don't have this increasing ripple in a low frequency area. But this is something that we want to have in real life because all rooms that we measure also have the tendency to sound like a pink noise or just lower level high frequencies. So this is better for our ears and have more in common with how we predict sound. And so let's mute this channel and add the noise with -5 dB. Then I have a ripple of ±12 dB. Same with -10 dB, and the ripple is gone to ±6 dB. That's a good real-life situation here for measurements. You should be able to measure your signal with such things. And if you think you get a straight line from your straight line speaker in a labo, then you are wrong, because the coherence, it's not 100%. You have this gezappel here, like Merlin said, and The next thing is I decrease the level of the noise anymore to -20, and this is almost perfect. Then you have a coherence here of 99%. It's the best you can achieve in a real life situation, because otherwise your measurement signal is too loud and then you don't have friends in the catering, and we all need them. So the next thing is I change the noise to a room signal, because in real life the room is adding also noise that is not inside of the pink noise from the generator. And the room has a high frequency damping, and also here the coherence is 100% because there is no room signal in high frequencies in this example, because I used here such a little plugin for this. And this is not a real life situation because we need room modes, and I can activate room modes here, and then you see this is gonna be very hard to tune my low frequency area here, because I read out just shit because of bad coherence, and I have to increase my measurement signal, which means I have to decrease the noise in this example, and then I can work with it. So, question: how to choose the right measurement level of your generator through your speakers? And I just switch on the noise and turn off the generator signal here, and you have to change from magnitude to real-time analyzer, and you see the noise floor here is at -72, and then I capture this and say this is noise, and then I switch on my generator over the speakers and adjust the level at my mixing desk that I have 20 dB over the noise floor, which means this is what I want to achieve with my coherence, that I can do a good job in measuring my system. And now I can switch back to the magnitude and see that here is a good coherence value, and it gives me a solid line, and I can do a good job. So next one is I want to add a sine sweep, just to show you how averaging works. Here's no averaging in the signal, and this is very hard for my eyes to follow what's going on here. And so I add some averaging, and there is a point that averaging doesn't bring any benefit, because in this example I can see nothing more. I go back to 16 first in first out buffer, and then I choose a magnitude smoothing of an octave, and you can see the coherence is walking through here, running through like from the sine sweep. So you can see there is some noise in the signal, but the magnitude don't show me the values for it, because I have too much smoothing used. And what this means, I want to show you in the next example. I'm measuring a speaker, and the speaker gives me a magnitude like this. And what do you do to correct this is you introduce a EQ. And perfect, I'm done, good job. But then it sounds like shit. And I switch back to 148 octave, and you see this is a problem, and this is my solution. Yeah, and that doesn't match perfectly, and bad job. So I can recommend to use 1/48 of octave, and when you start measuring, your eye might say, I don't like it, I don't understand it, but you have to get used to it, and it doesn't take long, and then your brain can do all the smoothing better than the software here. But let's see this later when we come to real life measurements, and not in this software example here. So everything muted. No, here's mute, and we come to the next exercise. This time we want to do a top sub alignment of our speaker. setup. So we have here a top speaker and a subwoofer system, and they crossed over at 80 hertz. We can see if we just have the subwoofer, here's the crossover, and also the top speaker is a crossover here at 80 hertz, and we have to bring it together. And for this example, I just leave the reference delay here, and therefore the magnitude is not the real magnitude. It looks bad, but you can ignore it. It's just because the reference delay doesn't match to our signal. But if I match it, my phase doesn't look that good to what I want to show you how this just works, because it's very simple, and sometimes people make it very complicated to talk about how to measure it, but it's quite simple, and I want to show you how it works. First thing is my top speaker arrives first, and my subspeaker arrives first, and my top speaker comes later because it's more far away. And the first thing is I capture the top speaker, and let's say here this top. I did the German version, and then the top English version. And so we have the trace, and then we mute the top speaker, go to the subwoofer, and we see it's not in phase, it's not in time, it's nothing. And if we switch on both systems, subwoofer and top, and they are not corrected, then you can see here this dip. And what is the cause for this dip? Correct. This is the COM filtering that we have in this exercise 2 here, and it's the same thing, 2 signals not in the same time, so they cancel out, where frequency is at 180 drift, 180 degrees shift. And the last third percent of the phase wheel, we have deconstruction and cancellation. So, if you're not an experienced user with measurement systems, you may take the wrong decision and add in your mixer or your DSP setup a equalizer to fix this issue. Let's capture insert this equalizer here. I mute the top speaker, and now we want to align the sub speaker to the system, and therefore we need a delay in the subway. And this is what I did here with the first delay. You can see here at 80 hertz they are perfectly matched with 0 degree phase shift and have perfect combination. But only at this frequency. And if I add the top speaker, you can see, perfect, my equalizer here does what it's made for, give me more signal. But at the other frequency, we have not a perfect combination, because we are in phase, but we are not in time. And in this example, I'm 2 times around the phase wheel, and in real life, we have to change this. How does it work? We add the delay, and then I'm increasing the delay until these phase slopes perfectly match at all positions in the area, and this might be here the case. And switch on all speakers. In real life situations you have to mute the top speaker. It's just here in the electronic way this worked, so this is my bug, sorry. And both systems on, you see there is a 3 dB peak here. This is because I didn't use Linkwitz-Riley filters, which can avoid this, but Logic is not able to set the low pass and the high pass filter to Linkwitz-Riley. So yeah, we have to correct this with another EQ, but that's it. first video. I hope you enjoyed it. Go to my website and download the setup. If you like the video, share it to your friends. Give me a comment. What did you like? What did you don't like? What would you see in the future? And in my next video, we go to the same measurement here, but with overlapping top speakers. Some manufacturers have presets that the top speakers are running flat, and then this combines with subwoofers, and we want to see how to match this and what this do to the combination in these zones. And then I want to show you the live impulse response. What do you see here? Which problems can occur if you use a network-based system and do an internal loopback and you measure with music? Well, some words about this, and then we're gonna measure a end-fired subwoofer setup and also a gradient subwoofer setup. And then I want to show you why the delay finder won't work for subwoofers. And I want to show you the difference in impulse response with a EER filter and an FIR filter. Yeah, I hope you enjoyed it. See you next time. Bye-bye.